Welcome everyone to QSI Virtual Seminar. Today, speaker is Dr. Christina Giarmatzi. She's a Sydney Quantum Academy postdoc fellow in the group of Professor Chris Berry at the UTS Center for Quantum Software and Information. Her project is on semi-definite and AI methods to characterize quantum devices. Christina has great experiences on topics like quantum causality, convex optimization, and non-Markovianity. And today she will be talking about a method to detect quantum memory in a non-Markovian process. If you have questions during the talk, please unmute yourself and let's start. Christina, please.
Thank you very much, Clara. So I will present this work that I did as a postdoc at the University of Queensland. This is a joint work with Fabio Costa, and here is the archive over here. And as Clara said, I'm an SQA fellow at UTS, QSI Seminar here. I'm working remotely from the Sunshine Coast, and this is the date, if you didn't know. So the motivation for this work is in general on the study of non-Markovian processes is in general that the fact that experiments are very difficult to implement. So this is why is this? Because you have always this interaction with environment, and the environment can be from various different sources and they can be correlated, and so there's a lot to take into account. And the problem is that we can't really describe what is happening in reality in an experimental setup, because usually you cannot describe your environment. So this is the study of open systems. And here in this picture, I took it at the labs of UQ, Quantum Optics Lab of Andrew White. And it just shows a source of pairs of entangled photons. These prisms are just tiny mirrors that deflect the photons in different directions to be detected. The purple thing is just fluorescent light. And if you look at the surfaces of posts and the crystal itself, you will see a lot of dust. So that is one source of environment, one source of noise. Well, it can affect your system. Of course, here we're talking about quantum systems, so there can be even other quantum systems that affect your system. Anyway, there's other examples of noise in your environment. So this, I guess, is possible in Queensland or in Australia in general only, but it can happen. So you need to find a way to characterize, hopefully not the bosons, but in general, your system with the environment. So the observation from this problem is that experiments are open systems. And the question that we particularly are asking is how to describe not any noise, but correlated noise in your experimental setup. So, and by that, I usually would refer to an environment that has memory, because you need to have some sort of memory that carries a correlation from one time step to another to have this correlated noise. All right, so here's the outline of the talk. I'm going to put the timer. So I will talk about another approach to open systems, and this is through the process matrix formalism. So I will describe basically Markovian processes and non-Markovian processes, namely the ones that have quantum or a classical memory through this formalism, the process matrix. And then I will present a way to detect a quantum memory in your quantum process. And finally, I will talk about some results that we obtained through this method that we applied on a particular example. So we're here, open systems with process matrices. So this is some representation of an open system. Here you have a state that undergoes through different transformations. This is a sequence in time. And for the system to be open, you need some environment as well. So you have all kinds of interactions. You have that the environment is might be affecting the state. So you would have some initial system environment correlations. You'll have that the environment is affecting all the transformations, and you might have also that these transformations, the way that the environment is affecting them, depends on something that happened before. So here it would depend on the correlations with the state. And over here, it would depend on what happened before, on the correlations in the environment with T1, but also what happened in the previous step as well, over here, and so on. So the way the environment can affect this transformation would be conditional on what it got from here and from here and from here. So I will just tell you about a few different quantum descriptions and what is their classical limit, just so that we understand better what these descriptions are providing. So one way to describe this is to just update the process matrix, to update the density matrix that you've got in the various time steps. So you can just measure your state here, measure your state here, your state here, and so on. And of course, this will not give you much information. This, in the classical limit, it will just give you some probabilities of some random variable x that is that's the value that it takes on some particular time, T0, T1, and so on. So another description of this open system would be through dynamical maps. So in this map, so in this description, the whole process is regarded as a map, as a dynamical map that maps the state from here to here, and from here to here, and from here to here. So in every step, you have a different map that maps the state, the input to the output state. And what that will give you is conditional probabilities of some random variable at time T1, for example, conditionally on the value that it had at T0. So it will give you some information between some correlations that you would have in your setup that would be from the previous time step. So you would have pairs of time steps where you would have information, some information. However, ideally, we want a quantum description that would give us the full description of in the classical limit, it would be the stochastic process. So we would have the joint probability of all the random variables given on all the different time steps. Right, and now I will present this process matrix formalism that will give this information. So you have here a process that only has two transformations. You have your state, transformations, and some measurement at the end. And in order to describe that, this formalism requires that you put some measurement stations in some parts of the process, such that you obtain information and you describe the process. Now, these measurement stations, they have input and output Hilbert spaces, denoted by AI as input, AO as output, and BI, BO. And these measurement stations are there to perform an arbitrary, completely positive map from the input to the output. So an arbitrary operation would be, for example, a measure and prepare operation. So it could be that A is just a box that measures the input, and conditionally on the output, which I denote with output A, A can prepare another state to send out. So there is this transformation from the input to the output system is defined by this map, and that has a tag of the outcome. So the result from this way of doing things is that, and that was the result of the original paper, is that the joint probabilities of the local outcomes here of the maps that A and B are implementing is a function of their operations. Here I have probabilities, a function of the operations that they're doing. This is the toy matrix of the map that is implemented here. This lives on the combined Hilbert space of input and output. Right, so the probabilities equal, it's a function of the maps that they're doing, the operations, and of course the environment that they are exposed to. And this environment is the description, complete description of the process that is all around the measurement stations A and B. And it lives on the combined Hilbert space of the input and output Hilbert spaces of the measurement stations. Any question over here? Because it's a bit, this is a bit new to people probably. There's something on the chat. Does a person count as an environment with memory? Yes, classical memory maybe. Yeah, it could. It was clever enough. It could. Any other question? No, oh, good. All right, so I'm going to use this formalism, and I will give you some reminders as well of what is going on, because I will use this formalism to describe my quantum processes from now on. Right, so now we go to how we can describe with this formalism Markovian processes and non-Markovian processes, and then the latter I will distinguish them between having classical and having quantum memory.
So maybe I will ask one question just before you move on, although you feel free to defer the answer if it'll become clear. Initially, kind of, we were referring to the Choi-Jamalkovsky matrices that we started to refer to that as the process matrix. It's just it was a simple, more generic thing, language that we were doing. I understand that Kavan Modi also has a or started using a kind of a matrix that he started referring to as a process matrix. Is that the same as what you're talking about here?
First of all, the process matrix is not a Choi of something. That the Choi was here, the operations.
Yeah, right. This is different from what we used to refer to as the process matrix. I agree, but but I guess my real question is how it compares with is it whether it's the same thing that,
yes,
that Kavan is looking at.
Kavan Modi refers to them as process tensors,
right?
And it's exactly the same.
Okay, right.
Same as a quantum comb as well. So these are I was supposed to say that these are the three different names that it appears. A process matrix is a bit more general, but in this case, it's exactly the same as the quantum comb and as the process tensor.
Okay, thanks very much.
Cool, no worries. All right, let's go to these Markovian and non-Markovian processes. So we use the definition of Markovianity that was introduced by Lindblad and Accardi et al. And was later adopted by Pollock et al. This is Kavan Modi's group in Monash. And in this definition, it just describes two cases of Markovian processes. In one case where you have no noise, you just have your state, transformations, and your measurement at the end, and nothing else happens. And in the second case, you have noise, but it's Markovian. This means that over here, there is an environment that can affect your system through this joint transformation. However, any information that the environment obtains about the system is not transferred into the next interaction. So I think I wrote it somewhere. I didn't. So basically, every system environment interaction is local and does not affect future system environment interactions. So this is a Markovian process. Now, how do we describe this in the process matrix language? So again, this is a Markovian process, rho, T1, T2. You have the local interactions with the environment, and you plug in these measurement stations in order to get a description of the process. So we define a process matrix of a Markovian process like this. So here I have just for you as a reminder of what is a process matrix. It's an object that you plug in and you obtain probabilities. Right, so the definition of a Markovian process is Markovian process matrix is such that it's a tensor product of the input state at first. It lives on the input of A, and then it's the Choi matrices of the channels over here that are used in the process. So if you would have more channels, it would be all the channels tensor product here, and then finally you would have identity on the output of the last measurement station. All right, so now let's see how we can talk about non-Markovian processes. So in a non-Markovian process, there is a memory that carries the correlations. So this would be a representation of a non-Markovian process. On top, it's the environment, and over here, it's your system. You prepare. So it could be such that the system and the environment are prepared jointly. So there are some classical or even quantum correlations between them. And it could be that the environment is going and it affects, there is a system and environment interaction here, and there is another system and environment interaction here. Every time there is basically a gate, there is an opportunity for the environment to affect the system. And this is just some sort of interpretation that the environment is taking information from the system, and given that it's affecting over here, and given that and that, it could be affecting over here. And then we ask the question whether this memory that carries these correlations, whether it can be represented as a classical memory or a quantum memory. Let's see. So this is how we represent a classical memory. You have your process, rho, t, and n, and then you have your environment here. And by this double thing, we represent that there is a transfer of classical information. So there are some classical correlations between them over here, in the sense that the environment has some classical information about the system. And it goes on, it affects, there's an interaction over here, and over here there is the classical information, some classical information about what happened over here in the transformation and about the initial correlations. And this can go on and on. So this is how we represent that the environment has a quantum memory and that the correlations it carries can be represented with a classical channel. And here are the measurement stations that we put in order to describe the process. Right, so the environment obtains classical information in every step and can affect future interactions. And I'm not going to give the definition that we provide for the classical memory, for the process with classical memory. That's because it's a bit complex. And actually, I'm going to use this one. So a process matrix, a process with classical memory can be written like this. This means that this is a more general form of the actual definition. So it's like a larger set of the set of the definition. You will see later.
Christina.
Yes.
How do I understand what role the memory plays? Is the memory something that is just able to condition the input state of the future environment, or can it also affect the nature of the interaction between the environment and the system? So can NJ also depend on this classical information?
Yes, that's true. So yeah, it affects the, so in this gate, they interact. So the state that comes out is different than the one that it would have come out if the environment was not there. So it actually changes. That this unitary is it's not necessarily unitary, but this transformation is conditioned on the environment.
Yeah, no, I guess that's not quite what I meant. So you've got this between your T and your N interactions, you've got this classical information channel.
Yes.
And my question is, do you assume that, so coming into the interaction N, you've got some transformation, which is described by N, and you've got some quantum system, which is defined by whatever the state is at the bottom channel, and then you've got some state of the environment, which is whatever is described by this top channel. And presumably, because this is a classical memory, at just before n, the environment and the system are again not entangled with each other, or at least that's how I interpret this picture.
Not in the quantum sense, however, there is some information. This environment over here carries information of what the state was initially. And
right. So my question is it, so this classical information, obviously it can affect the state of the environment just preceding the transformation n. But my question is, do you assume that the classical information about the past, the classical memory, can also affect what the nature of the environmental interaction n is? Like, does it change? Can nj depend on the past, the classical information about the past in the environment about the past, or is it only the state of the environment that depends on the past information?
Right, but the state of the environment is affected from the past information.
Yeah, no, that's clear. But is n also affected by the past information, the actual transformation that's implemented?
I think so. I mean, it just depends what we mean, but I don't remember exactly what I meant when I drew this thing. But let me think. State. Well, this is what I said in the beginning, that I think that yes, it is affected by the environment, because the environment has a different state. And also the system environment, right? So whether the system environment interaction is affected by the state of the environment, I don't know. I can say yes, I can say no.
I mean, obviously the outcome, the output state will be affected by this, but the question is whether the actual transformation, the matrix describing that nj is also a function of this memory.
Yes, I think so. Yes, because okay, so the way we wrote the definition over here, these indices depend on the previous indices. So the whole transformation really depends on the previous transformation and on the information on what happened.
Right. Okay. So that can be captured by the formalism.
Yeah.
Okay. Thanks.
No worries. Any other?
But like looking at the diagram, it looks like the information is just input to the channel, right? The nj. You have some measurement outcome and you prepare some states, and that's some input to the channel nj, and nj doesn't really depend on like the matrix of nj.
Yes, the way I put it over there, yes, but yeah, I couldn't. Maybe I should have put just n and t.
Okay, but you're saying that the formalism actually can handle the more general situation where nj.
So basically, nj here, it depends on everything that the classical information, the classical.
Yeah, well, I think like these two setups are different, you know, because the latter one is more general.
Yeah, I guess it's hard to draw in a simple picture that
This first setup, it's like you are programming the channel using some input. Otherwise, like in the latter setting, your
I guess
the channel itself is depending on the parameters of the measure in previous round.
Yeah, so it's a sort of a dynamical circuit. That's why it's hard to draw, because these things will change in every run. Because it's a conditional interaction.
So if you like, there's some sort of classical feed forward directly onto the nj box as well as the state of the environment.
Yeah. Yeah, so maybe I couldn't. All right, we'll see. I will draw it next time. Anything else? All right. So now let's see how we can talk about the quantum memory, we can't really say anything. We just say that it's everything else. So a process matrix that cannot be written as a Markovian one, so the tensor product of all the different things, and a process matrix that cannot be written as a one with classical memory, it would be a process matrix with quantum memory. And I just describe it like this, in the sense that it could be a joint state. This is a quantum system, obviously, and there is just joint transformation. Again, I guess there would be the same problem, how to describe the next one given the previous. So maybe this is better. I just put T and anyway. All right, so now we go to see that there is a method on how to detect quantum memory in a process. So remember, a process with a classical memory can be written like this. And you can observe that this is the set of separable states. That's why I chose this, this more general form than the definition. So this means that the definition of processes, like the processes with classical memory, is a slightly smaller set than this larger, but that's okay. That's good enough. So all these things are positive semi-definites, because these are Choi matrices of CP maps, and this is positive, and this is positive. So it's the same as the set of separable states. So this means that if there is a point that is outside, if you look at it from the process matrix perspective, it's a process matrix that has a quantum memory, because it's outside the set of the classical memory. And if you look at it from the perspective of the states, then it's an entangled state. So this is our main result, the fact that using the process matrix formalism, we could write down the process with a classical memory as a separable state. And so everything that has a quantum memory can be detected in the same way as you can detect an entangled state. So we just mapped the problem of detecting a process with quantum memory to the problem of detecting an entangled state. And this is a well-known problem. So what you can do is you can apply any method of entanglement detection to detect a process with quantum memory. So this is what we're going to do. I'll just present one way of the entanglement detection. And one way.
I have a question about the previous slide. So it looks like when you have written down W in this form, NJ matrix cannot depend on outcome of previous process. Like if TJ is a measurement, there's certain outcomes, then NJ cannot depend on the outcome. It's related to the previous question. Right. Like the channels, the matrix of the channels in later process cannot depend on the outcomes. It just takes the input of.
Right. So the original definition in these indices, they depend on the previous one, but the larger, like that definition can be written as this. And in this case, you have these indices that they don't depend. Like this is the form.
Okay. So J is the index of classical measurement. Okay.
So in this case, this is just one index, and you sum over all the indices.
Okay.
As a separate state. Yeah. Okay, so one way of entanglement detection is you have the convex set of separable states, and something outside is an entangled state. And by the hyperplane separation theorem, you have that there is a hyperplane that separates the entangled state from the rest of the convex set. And this hyperplane is called a witness. And a witness in this language is an operator that you can apply it on the state that you want to find whether it's entangled. And if you get a negative outcome, a negative expectation value, then you say that this is a witness for that state because you have witnessed entanglement. So this will hold true only for an entangled state when you apply an operator and you get a negative outcome. However, so this is a very nice way of detecting entanglement. However, for your method to be successful all the time, you would have to characterize the set completely. And the problem is that the set of separable states cannot be characterized completely. We don't have a complete description of it. So instead, there are some separability criteria, which is simple conditions that hold for all separable states. And so these criteria, they are hierarchy, they form a hierarchy. So sometimes one criteria is stronger than the other. So you can use various different criteria to test entanglement. And I'm going to talk about a few criteria. So the first thing you will do is you do the simplest criterion ever, which is the PPT criterion. So this was introduced by Perez, and it just means that if your state is separable, then the partial transpose over one, if you have two subsystems, for one of the subsystems is positive. So this is a condition that always holds for separable states, and we use it to characterize the set. So if this was ABC, then I would take the partial transpose over TA and over TB. So basically, because rho is positive, and if this is positive, over B is also positive. So you don't need all the partial transposes, you just need all of them minus one. So now how do you find a witness using this PPT? So there's a simpler way to do this using this criterion, but I will talk about the semi-definite program because the next criteria will also use the SDP. So SDP is just a way to formalize convex optimization techniques, convex optimization problems. And you can do it in Mathematica, MATLAB, or Python. And what you write is that I have this variable Z in the sense that it is unknown to me. Minimize this thing, minimize the trace of the variable, this witness that you want to find with the state. So minimize this matrix, the trace of the matrix with the state, because we want to find something that is negative. This is just a condition to avoid infinities. And you run the problem. And if it finds that the optimal value that it found was negative for some operator, then it means that this operator is a witness because it satisfies the description. And it's a witness for this entangled state. All right, so let's say that you had a state and you wanted to test entanglement and you tried the PPT and it didn't work in the sense that you did not detect entanglement. So it found that the minimal value is still positive of this of the trace of the Z with the. So it doesn't mean that you should give up because your state could still be entangled, but just was not witnessed by this criterion. So what you can do, and this was something that was introduced by Doherty, Parillo, and Javaherian, you can extend the state. You can write a symmetric extension of rho, so A, B, A prime. Here rho is AB. And by symmetric extension, I just mean that if you trace A prime, you end up with the original state. And also this state is symmetric under swap of A and A prime. So if rho is separable, then there exists a symmetric extension of rho such that this symmetric extension is separable. And then you apply PPT and you have these conditions. So now you have more conditions. You don't have just that rho is positive and rho TA is positive, but also if rho is separable, you have more conditions. And this is helping you to find a witness because then you write the SDP and you say, so here you don't minimize anything at the moment. You don't want to find a witness. You just want to see if the state is entangled. So you write, find an extension of rho. So a variable is rho but it's also an extension, so it has this swap and trace properties, subject to this that is positive. So every one of these is positive. So basically, you have a state and you ask the STP, find me an extension of rho such that this extension is separable. And if the output is yes, okay, I did it, then it means you have not detected entanglement. But if you cannot do it, if the problem turns out to be infeasible, then you have detected that this state is entangled. And then what you can do is you write a dual problem of the STP where you find a witness for rho prime with the same way as before, just minimize the trace of Z with rho prime. And then having the witness for rho prime, you can construct a witness for rho. So there's a plus and minus for this STP thing. One is getting more expensive because you extend the state. So you have to deal with convex optimization techniques with larger and larger states. And it's not an easy algorithm to run. So for example, I had a 3-qubit state and I ran this PPT tool and it took me 7 seconds for each outcome. However, the good thing about the STPs is that when you ask for something, you can tailor it to your expectations. So if you are doing things in the lab and you want to have some particular operations that you can do to the state to witness it, then you can say to STP, I want a witness such that it's composed out of unitaries, or it has only some particular measurements. Right, and then you have a witness with this dual. Okay, so if you still have not detected entanglement and you really, really want to do it, then you just keep extending the state. You take a symmetric extension of the previous symmetric extension. So now you have a double prime, which is the copy of A. By the way, you can do it with B as well. And then you have that if rho is separable, then also there is a double symmetric extension of rho that is also separable. You have more conditions to put. So this, you can do it forever. So this means that what Javaherian et al. Did is they provided this separability criteria, which first of all is a hierarchy. So you have PPT1, which is the first step of the hierarchy, which is the traditional PPT. And then you have the second step of the hierarchy, which is at least as strong as the previous. And then you have the third step, which is at least as strong as the second step, and so on. So you have this, this property, and another property is that this family of separability criteria is complete, which means that this method will always find a witness. However, it's not easy to just go on extending the state because, as I said, with 3 qubits, with a 3-qubit state, it already took 7 seconds. So with adding one more, this grows exponentially. So it's not easy to deal with larger states with STPs. However, it will definitely detect entanglement at some point. Anyway, in case you got lost, just a bit of recap of what has happened so far. So we have the process, and we describe it using these measurement stations over here to obtain the process matrix, which is a matrix that gives us the right probabilities for the outcomes of the measurement station over here. And then we wrote a process with classical memory. We wrote it like this, and it's in this language, it's the same as the set of separable states. And because of that, we could detect quantum memory through detection of entanglement. Any questions so far? All right. Now, let's see. So in case you didn't know about witnessing of things, let's see, let me tell you what to do with the witness. So a witness, as I said before, is an operator such that the trace with the state that you want to find it entangled is the expectation value is negative. So if rho is a state, then what is happening is that you're in a situation where you don't know the state and you don't want to do tomography to find out the state. So it's in the lab and you don't want to do that. However, you do want to know if it's entangled, so you want to detect entanglement. So what you do is you make a guess for row. You try to find the state that is the closest to the state that you have in the lab, and you find a witness for that row. And the witness, remember, is an operator that you apply on the state. So you have the witness for row, you applied this operator to your experimental row, and then if you get a negative exploitation value, then you have detected entanglement. However, I have mapped states to processes back and forth. So if you have a process matrix that you write it in your computer as row to find a witness, however, it's a process matrix. So you're in a situation where you just don't know the process. You have an experimental setup in your lab and you don't know the process. And of course, you don't want to do process tomography. However, you do want to know if there is a quantum memory in your process. So you make a guess for the original, so a W prime, and you find a witness. And a witness for W prime would be operations that you need to do in the process. So you go to your lab and you insert those measurement stations that you would have anyway to do tomography, but you don't want to do tomography. So you just do a limited amount of operations on A, B, and C. And that would be the witness. So this operator, you apply it on the process where you go to the lab. And if you get an expectation value that is negative, then you have detected a quantum memory in the process. Any questions for this? Okay. All right, now let me tell you some example where we apply this method and what are the results we got. So on the example that we have is just a small process where you have above is the environment and here is the system, and you have that environment and system prepared in the maximally entangled state. Here should be 5+, and this is the state. And then later they interact according to the Ising model. So you have these parameters J, H, and T. T is the interaction time. So the Ising model is a model between dipole-dipole interaction. So T is the time of interaction. And here J is the strength in which the two dipoles want to align in the X direction. And H is the strength of the external magnetic field that they want to, that it wants to align the dipoles on the Z direction separately. So this is the process matrix. It's a process matrix that depends time of interaction, strength of the magnetic field, and the strength of the dipole-dipole interaction. So what we did here is that we set the interaction time equal to 1. We took a process for every J and H. So J the interaction and H the strength of the magnetic field. And here is a heat map. So every pixel is a process matrix with a particular J and H. And then through the PPT criterion, we found the minimum value of this. And whenever this minimum value is negative, then the process has a quantum memory. So in every other case other than the yellow parts, the process had a quantum memory for that J and for that H, and for T equals 1. So I applied just PPT for that, and I applied the second step of the hierarchy. So I applied the PPT2. I didn't do it for all of it because, as I said, every pixel here is a process where I have to find whether there's a memory or not. And the STP was taking 7 seconds for each trial. So, however, I just did a small area over here, and I tested the PPT2, and it gave the same results. So this means that every yellow part, entanglement was not detected. So a quantum memory was not detected. And this means that there could be a Markovian process or a process with classical memory. And what we did is that we realized that we can find the Markovian points, because for every process, we can take the relative entropy of the process with its respective Markovian, with its equivalent Markovian, and find out that if the relative entropy is 0, then the process is Markovian. So these are the Markovian points. And just to compare, the points where the lines cross. Oops. Right. So this means that these points are the Markovian points, and everything else is something that we have not detected quantum memory. So it's either classical memory or quantum memory that we did not detect with PPT-1 and PPT-2. All right, and since I have some time, I can talk about this next step that we did on this project, which is some work that we finished recently. So what we wanted to do is to do something in the lab with this project, so to detect the quantum memory. And we thought at first, okay, maybe we should try with a classical memory first and see what happens. However, as you know, this method does not detect classical memory. It only detects quantum memory. But we thought to still try something. So the aim was to infer non-Markovianity, so some measure of non-Markovianity only with classical memory through machine learning or polynomial regression. So we have in the lab raw, and we have a unitary here, and another unitary here. And we also, here the measurement boxes, this is just a unitary, so it's not informationally complete operation. And here is some state homography. So the process is this, and we have an environment that correlates K and L, because this is a classical correlation. So basically, we didn't obviously do that. We just simulated, we just correlated K and L artificially. We just made them correlated with some degree of correlation. And the point is that we wanted to infer non-Markovianity by just taking experimental data from here and here, but incomplete experimental data. So we didn't want to do tomography. We wanted to just have less information. So state homography is only here, and here is just a unitary. So the result was that with about 100 points from incomplete operations on A and B, we get a prediction of the measure of non-Markovianity. So for a measure, we used the relative entropy of the process with the corresponding Markovian process. And the result was that we just used polynomial regression because it was doing as good as the machine learning, even a little bit better. And the model can predict with accuracy of 92% the measure of non-Markovianity given the data from A and B. Okay, and some final thing is what I'm going to do as a next step of what I presented. So basically, I will take these methods to the next level, and it will be through STP and machine learning. So through STP, I just want to have a software that, so this is my computer. So I just want to input to the software an arbitrary quantum circuit, and I wanted to use n-step PPT criterion, and I wanted to detect whether there is a quantum memory. So first I will do that. However, this has limitations depending on the memory of your computer. And for these cases, I wanted to have a machine learning part where it takes larger circuits, because it can deal with, it's not a convex optimization anymore. So it can deal with larger matrices. And or it can just have incomplete data about the process. So not even the process matrix itself or a guess of it. So even less. And through some machine learning magic, I wanted to output a quantum whether it detects the quantum memory or some measure of classical memory in the setting. So that's it. So what I've done is I've told you a new way of looking at open systems through process matrices. And through this description, I wrote what is a Markovian process and what is a process with classical memory, and how to detect quantum memory through this description. And finally, some pretty pictures with the results on an example we had, the work in progress, and my project. And that's it. Thank you.
Okay, thank you, Christina, for the great talk. And I clap on behalf of all.
Okay.
And now, if there's any question, please unmute yourself.
Christina, I have a question. In thinking about like applying this in real quantum devices, like for example, in real practical scenarios where people are trying to build quantum computers, build qubits, can you imagine maybe some special class of these process matrices that allow you to do these calculations faster? I guess like ones that maybe the hope would be, you know, adding assumptions which are closer to the experimental realities might make it easier. I don't know.
I didn't understand the final part, but it's not. No, I don't really think of classes of processes that would work better than others. No, any process where you basically have entanglement between different parts of your setup. And if you can write a description of that process, if you can write the process matrix or a close enough process matrix, then you have it. If you have the matrix itself, then you can detect it. You can find a witness, and the witness would be what you need to do in the lab. And if this is not realistic, then you need to tailor your witness, and you need to ask PSTP, can I find a witness that has less measurements? For example, for that particular example that I used, I asked if it can find a witness with just unitaries, and it didn't. So, but you can have things like that.
Okay.
So just following on from that, are there with non-Markovian processes, are there any sort of structure or symmetries that you might expect such processes to have, still be non-Markovian, but to have some sort of simplifying symmetries?
So they have symmetries because you mean they have a quantum memory.
Well, I guess I'm just thinking about wondering if there's some in realistic scenarios where there's a sort of a way that the information might be retained and stored in the environment in such a way that sort of simplifies the description of that memory-like process. So as you say, maybe there's a simplish quantum memory that just feeds back directly into it or what, but are those sorts of things sort of at all common when you're thinking about non-Markovian memories, or is it really just anything and everything is fair game?
I would think it's everything and anything, because when you look at the process, you look at what's happening to your state, to your system. So the environment is just going to add correlations in your system, within your system. So all you see, you don't really see the environment, you see the reaction, the effect of the environment. And over here, for example, I should have said that when you have a quantum memory, so this is your process, and the state, the equivalent state, is a bipartite state where A is AI, and B is over here. And then there's entanglement between A and B, so between that part, AI, and between AOBI. So if you look at here, there is entanglement between over here and the channel over here. So this is the signature of the quantum memory.
Okay, thanks.
Maybe you have already discussed the motivation for considering classical and quantum memories, but can you give more discussions on that? Like why should people care about whether it's quantum or classical memory? And
Right.
is it like quantum memories are much harder to deal with? What's the motivation?
Right. First of all, Kavan did a work on trying to find a quantum memory in the IBM experience, and they did. So there was non-classical correlations among the various steps of the circuit that the IBM coding experience is using. So the point is that you have a setup, and if it's, for example, quantum optics, then it's probably the case that there is no quantum memory, because for quantum memory you need another quantum system. So you need another photon to go there and entangle with everything, which is usually not the case. If you have ions or something, then you would definitely expect other quantum systems laying around and getting entangled with the state that you want and getting entangled with the future time steps as well. So why would you care? Because then you would know, for example, if it's classical or quantum, then you might have an idea of where you should start to correct this, to deal with this. So I think it gives you a very good indication of where your noise is coming from. If it's classical, then you know where to look for. If it's quantum, you definitely know that you should look somewhere else.
Okay, thank you.
So if there's no other question, let's thank Christina again and finish the session.
Awesome.